So let's talk about a concept that I feel kind of gets glossed over in organic chemistry, and I can totally understand it. It's kind of a niche reaction, but it does illustrate a very important concept in organic chemistry, and this is the idea of a protecting group. So here we're going to talk about acetals and hemiacetal compounds, and the way we make these is we react an aldehyde or a ketone with an alcohol. Now, what's going to happen? Well, let's go back to our HX analogy. H here is going to be the H plus, and the X here is going to be our alkoxide ion. Now, as you expect, the alkoxide here is going to attack the carbon, promote the double bond to a single bond, and give us a lone pair that will subsequently attack the hydrogen. And this is a reversible reaction. So we end up producing an ester adjacent to an alcohol, and this here is going to be our hemiacetal. Now, if we just had equivalents of alcohol and aldehyde, this is what we'd expect to get, and this is a reversibility error here. So we would want to dry this by adding more alcohol, but here's the problem: the more alcohol we have, the more likely we are to drive the second reaction, also reversible, which is the reaction of this hemiacetal with the same alcohol to give us the acetal. So what will happen in this case is we end up making water. So if we add sufficient excess of this first alcohol, we're going to end up generating a second alcohol, and these geminal ethers to give us the acetal. Now, this is much more favored for an aldehyde over a ketone. So if this R prime here was an H, we'd be more likely to drive the reaction. Why is this important? Well, if we run this reaction, this is actually very stable under basic conditions. These esters here are not very reactive. So if we have an aldehyde or a ketone, and we're running reactions like hydrogenation on another part of the molecule, we don't want the aldehydes or ketones there because there's going to be the issue of how do we keep them from reacting with our reagents that we want to react in other parts of the molecules. Esters here are pretty stable. So if we make the ester, we make this acetal under basic conditions. We'll end up with these geminal diethers that will pretty much be unreacted to a lot of the other things we would do under basic conditions. We can react with other parts of the molecule, and then when we're ready, because this is a reversible reaction, if we add hydrogen, we acidify it, we'll get back to the aldehyde or the ketone. So this is a major advantage. If we make the hemiacetal or the acetal compounds, they basically remove our ketone and aldehyde groups in such a way that they can be easily recovered, but also remove them in such a way that they can't be reacted with other reagents. So this is the use of the hemiacetal and the acetal reactions. They create what are called protecting groups. These acetals and hemiacetals here don't react, and we may make it very easy for us to recover these aldehyde and ketone functionalities in a subsequent step.